Greeting from Champaign, Illinois. My name is Milton Feng. I'd like to take this opportunity to thank you, OPTIC committee, for this opportunity to give a talk on the topic of microcavity laser that changed the world. The outline of my talk, including from development of the transistor leading to the development of LED and the laser, and scaling of laser cavity down to ultra-low power operation today, and a future scaling microcavity laser. So in 1947, a point contact transistor was realized. The critical experiment worked the first time by John Bardeen and Walter Brattain at the Bell Laboratory with an overall power gain of 20 dB, 10x, on December 16, 1947. They established transistor operation principle. First, the minority carrier injection into this N-germanium-based semiconductor as an emitter current. Some of the injector electron excess hole in the base can recombine with excess majority electron in the base to release energy, which can be photon or phonon, depend as a base current. Finally, the rest of the injector carrier holes are transferred through the base without recombination, and the hole leave the base as a collector current. So obviously, 47 technology transistor integrated circuit has revolutionized the world, and the Nobel Prize of Physics was given in 1956, shared by Walter Brattain and William Shockley. So the history is basically saying that 47, Bardeen and Brattain worked without a Shockley, succeeded in creating a point contact transistor that's achieved the amplification. Shockley took the lion's share of credit in public for the invention of the transistor, which led to a deterioration of Bardeen's relation with Bill Shockley. Subsequently, Shockley forced Bardeen out of semiconductor research at the Bell Lab. And fortunately, Bardeen joined University of Illinois Physics Department and EC Department faculty, established Semiconductor and Superconductivity Research Group. In 1972, John Bardeen shared the second Nobel Prize in Physics on BCF theory of superconductivity. I believe he's the only person ever received a 2 Nobel Prize in Physics. So the first semiconductor LED laser was developed in 1962 at the General Electric by Honeck and Iron Ho. So the first infrared gallium arsenide PN junction diode was developed by Iron Ho at the G in 1962. And then months later, alloy semiconductor laser with a visible gallium arsenide phosphide was developed by Nick Honeck Jr. Both of this light emitting diode then was commercialized in 1963. Now, the reason why you need to do laser experiment is because you can extract in the efficient operation of conversion from electron to photon energy. Because the crystal have a high index, so have a lot of total, have a difficulty to get a measurement. Unless you can make a laser out of it, then you can have a light conversion efficiency being measured correctly. And subsequently, another major breakthrough is 1977, the quantum Modal laser. So in 1977, Honeck's group developed the first quantum Modal laser by LPE at the University of Illinois. I was a graduate student there. I witnessed of this development, and it's one of the very exciting moments in my life. So in 1978, Honeck with Ross Dupree at Rockwell which work on MOCVD system, demonstrate the first room temperature CW operation of the quantum well diode laser. Today, every LED and diode laser incorporate 3-5 alloy semiconductor in the quantum wells. So Professor Honiek have a lot of work being incorporated in this case. So looking at the cavity scaling in semiconductor laser. So as we see here, the picture demonstrated here, alloy semiconductor laser LED was 1962. Commercialized infrared and IR was 63. The improvement by heterojunction confinement and the bipolar transistor was 1969 by Herbert Kromer and Afurov. Current injection quantum well laser was 1977 by Honiek and Russ Dupree, 1978, quantum well laser. Current injection surface emitting laser was first reported by EGA using metal cavity. And later, with some DBR, they demonstrated 1989 for room temperature CW operation 10 years later. And the VCSEL with an integrated semiconductor mirror, top and bottom, plus quantum well was done by Jack Jiu in 1989. An oxide confined aperture edge emitting laser was first developed by Honiek and Dalasashi for the oxidation process for carrier confinement. And then subsequently in 1994, the first oxide aperture low threshold, less than 0.3 milliamp, was developed by Debbie. And 2002, the first commercial oxide VCSEL optical link was developed at HP Agilent by Fred Kish. This chart is modified based on Professor C.H. Wu from National Taiwan University. So vertical cavity scaling to surface emitting laser. So when laser was developed, it was edge emitting laser. So the cavity mirror is defined by cleaved facet. So mirror reflectivity is approximately 30%. So we need a long cavity, long laser cavity in Z direction, more than 200 micron or 2 millimeter, which is more than 1,000 lambda of the wavelength of the laser. So change to vertical cavity surface emitting laser, we employ 2 dBr mirror, which is allow you to have 99.5% reflectivity. This reduce the loss and shorter the cavity length can be reduced down to less than 5 wavelengths, 5 lambda. And today we can scale down to 0.5 lambda on the cavity. So the small cavity lead to a laser size reduction, low threshold, low power, and high speed capability. So the vertical scaling is not enough. We need the cavity is a 3-dimensional, so we need a lateral scaling oxide aperture developed in 1994, which is truly make a low threshold, the current less than achieved at a 0.23 milliamp by Dennis Debbie. And so this development is the first time we see a microcavity laser was being done, both carrier and the photon confinement. Lower threshold VCSEL was demonstrate reliability, open up truly energy efficient data transmission at a high speed. So this 1994 is a critical moment of the microcavity laser was first developed. So today, in our laboratory, we show a 1 lambda cavity oxide VCSEL can have a threshold as low as a 0.13 milliamp in the right-hand side here. And we show 3 different cavity size from large to small. And you can see the threshold current can scale down from 0.82 to 0.13 for the same material. And you can also see the separation of fundamental mode and first order mode by more than 40 dB difference in the small cavity. And this also to see the cavity mode reduce as a cavity getting smaller, available cavity reduce on that, and get into the Purcell effect on that. So for half lambda cavity, 850 nanometer oxide VCSEL, today is already can deliver 57 gigabits error-free data rate. So in the left-hand side, we see the multi-mode VCSEL with the 3 major spectrum, fundamental mode, 2 first-order mode, and 3 third-order mode pop out. And the right-hand red is 85-degree C operation. In the right-hand side, demonstrate error-free transmission with 5 terabits of data transmit without error of less than 10 to the minus 12 rate on that. The corner is the eye diagram of the device. However, the multimodal VCSEL suffers some transmitting distance problem due to dispersion, limited signal integrity over the OM4 fiber. So in the left-hand side, we show the multimode VCSEL and the transmit 300 meter OM4 fiber. As you can see here, there's approximately 3 different rising time, which correspond to the 3 different mode. The mode transmit a different speed in the fiber. In the right-hand side, we have single mode VCSEL, and it's showing after 300 meter, we have only 1 rising time. So the eye diagram is very clear, and eye-opening signal integrity is much better. So we realize single mode VCSEL can be very useful for longer distance transmission in OM4 fiber. So subsequently, we developed a new technique called integrated mode selective filter on top of the multi-mode VCSEL. So that allows us to have a single mode VCSEL operation. This technique allows you to show here the single mode operation can be achieved from room temperature all the way to 150 degrees C. The left-hand side shows the power level over the current level. In the right-hand side, it shows the single mode operation up to 150 degrees C and with cavity shifting, of course. However, the side mode suppression ratio is greater than 34 dB. So this is a remarkable stable device operation under single mode. So the single mode advantage, of course, is demonstrate the record speed over distance up to 1 kilometer. So in the left-hand side, we show the NRZ operation at a 7 milliamp. The device be able to reach 44 gigabits at 300 meter, 44 gigabits at 500 meter, and 38 gigabits at 1 kilometer. These results are the world record data rate over the distance in the OM4 fiber, okay? So in the right-hand side, we show the 32 gigabaud PAM4 data at a 500 meter room temperature and the 32 gigabaud over 1 kilometer at room temperature. They all pass a requirement on that. So as you can see, that single mode VCSEL, development single mode VCSEL can continue improve record speed and distance up to 2 kilometers. So furthermore, we collaborated with the National Taiwan University, Dr. Guangru Lin's group, and demonstrate the 16 QAM OFDM, the data rate up to 104 gigabits per second. So single mode VCSEL do have high modulation data form, and we're delighted to have a very good collaboration with the National Taiwan University. So record speed, NRZ speed to distance demonstrated in this view graph here. We plotted the best reported results, NRZ without the equalization and FEC correction. So you can see that at a short distance, our highest data rate is 57 gigabits per second. And our device pretty much can reach that level today. And of course, further improvement can be made on those devices. At 100 meter, you can see the highest data rate is 54 gigabits per second. And for some of the reduced mode and higher order mode. So as the distance go higher than 300 meter and above, you can see we hit the so-called OM4 EMB limit, which is 4,700 megahertz time kilometer. So as the green line here, and this line pretty much used by the data center today. In the right-hand side of that fiber limit is we have demonstrate reduced mode and also the single mode VCSEL. You can see the data rate can increase up to 46 gigabits at 300 meter and up to 44 gigabits at 500 meter and 36 gigabits at 1 kilometer. So as you can see that scaling will continue to improve that rate as we improve the fundamental mode quality factor on the device. So VCSEL definitely data link changed the world today. And as you can see here, VCSEL has a short cavity, lower threshold, higher bandwidth, lower cost, high yield, easy fabrication and testing, suitable for low power short range, 1 to 500 meter transmission. DFB edge emitting laser, long cavity length, high threshold, and high output power, mainly deployed in the long haul, 0.5 kilometer to 1,000 kilometer fiber system. So future research in a laser scaling cavity, and we just based on 1960 Hermannstadt's laser electron photon coupling equation. So in the left-hand side, we show the plotting of optical bandwidth response versus a frequency response. So the key parameter here is the electron hole recombination lifetime, tau B. If we see the recombination lifetime is 1 nanosecond, 1,000 picosecond, then with a resonant frequency peak is 7.5 gigahertz. As if we can reduce recombination lifetime to 300 picosecond to 30 picosecond to 2 picosecond, we can see the bandwidth increase in 3 dB bandwidth increase can be up to 150 gigahertz. So it's point out the direction that we can improve the bandwidth of the laser directed modulation laser if we can reduce the electron hole recombination process lifetime. On the right-hand side, show the signal integrity issue that the data rate, the ringing of the data limited eye opening. So if you reduce the recombination lifetime, it's also allow the eye opening to be clear. So it's further improve the signal integrity of the device. So two conclusions here. One is reduce the threshold current, allow you to get into ultra low power. So lithographic VCSEL is one of the things we're going to discuss for ultra low power operation, and reduce a tau B, which is electron hole recombination lifetime, like a transistor laser, can lead in bandwidth greater than 150 gigahertz for current modulation. So lithographic VCSEL, first demonstrated by Dan Steppe 2015. Fundamentally, he tried to solve a problem of heat transfer that oxide VCSEL, oxide confined VCSEL had a limitation of increased self-heating in junction temperature. So they block the heat transfer with the oxide layer in between the semiconductor. So if he choose to using lithographic defined cavity, then regrow the upper mirror on the top And as a result of that, we call it graphic VCSEL. In this case, there's no oxide aperture requirement. And you can see the laser operation for less than 4 micron VCSEL and down to 1 micron VCSEL. And the device seems operating very stable and have 2 to 3 times more power than the thermal limit oxide VCSEL technique. So these results allow us to further scale the aperture cavity down to 1 micron or sub-micron as we need it in the future scaling of our energy per bits data rate. Cryogenic VCSEL is another very interesting research area. And in our group, we work closely with Dennis Debbie, designer cryo VCSEL. And this is the first demonstration this year that we demonstrate 6 micron oxide VCSEL allow you to have a bandwidth at the 82.1 degree K at the 2 milliamp. You can see the bandwidth already exceeding 48 gigahertz. Furthermore, the plotting here on the green curve and the blue curve is fundamentally limited by our detector setup, that our detector did not have enough bandwidth. And so therefore it's a saturate limitation. So pretty clear that the device are capable to operate over 100 gigahertz bandwidth at a low temperature. So you can see at a very low current, you can already have 48 gigahertz over 100 gigabits per second operation. So that indicating at a low temperature operation, we may see a lot of new energy per bits and a lot of new physics in laser, improve the energy per bits transfer. Finally, we want to discuss a new device called quantum wave transistor laser that was invented by me and Professor Honiak in 2004. Fundamentally, we realized in high-speed HBT, indium gallium arsenide phosphide, indium phosphide HBT, you can have a speed up to almost terahertz. So when I realized that in 2003, Professor Honiak and I decided to put a quantum well inside of the base, in the base of the HBT device. And that will allow you to see some carrier confinement and have enough photon density to produce enough photon inside of the cavity and allow the laser to operation. So in 2004, we took this idea and realized that reported the room temperature or CW operation of the device. So the collector IV in this transistor laser obviously have a clear optical spectrum. However, the quantum well also demonstrated the transistor is operating from spontaneous recombination into stimulated recombination. So in this collector IV curve here, we see the red region outline a transistor spontaneous recombination. As transistor operating into a laser mode, and you can see the IV collapse compression into the yellow first ground state laser operation, and to a green, which is a first excited state operation, which is a half stimulated recombination rate. Therefore, compression, the collector output, so-called beta compression effect. As further apply voltage, we can see the collector junction start introduce of the so-called intracavity photon system tunneling, absorbing the photon in the device, allow the current to further increase. And finally, when the photon was reduced down below the threshold, then we have the spontaneously recombination process in the blue region. So this collector IV is the first time to map the quantum transition in a collector IV curve as a beta compression. Finally, I want to talk about in direct modulation, the first time we be able to see direct tunneling modulation transistor laser. So photon generate at the base and then traveling inside the cavity, and we can use a collector junction to form absorption of photon system tunneling. However, this photon system tunneling is different than typically detector tunneling. This device actually is inside of intracavity, is a cavity, inside the cavity. So the modulation efficiency is very high. And so not only highly modulate eye opening depths, it's also had a bandwidth much faster than can be reached over 200 gigahertz due to the 50 femtosecond modulation tunneling process. So in conclusion, from transistor to, we discussed from transistor, electron hole recombination leading to the energy release photon in LED and laser in 1962. We demonstrate scaling of the laser cavity for ultra low power operation. We show the vertical cavity scaling, and we also show the lateral cavity scaling, allow the finalized oxide aperture VCSEL to be less than 1 milliamp threshold current. This oxide VCSEL basically changed the world in data center and 3D sensing. So feature scaling of microcavity laser, we demonstrate the lithography VCSEL can reduce the cavity volume down to nearly less than 1 micron or less. And the cryo VCSEL increases bandwidth above 100 gigahertz to be less than 50 femtojoule per bits. Finally, tunneling modulation transistor laser can be very important research area, can fundamentally reach toward the 10 femtojoule per bits. We like to thank you, everybody, to listen to this talk. Also, in my career, I experienced considerable help from not only my 11 years stay in the company at the Hughes Ford, allowed me to learn the gallium arsenide microwave integrated circuit and digital integrated circuit at University of Illinois since '91. I have established millimeter wave and terahertz transistor research and for 5G wireless. I also did transistor laser and VCSEL research for data center and 3D sensing. I like to appreciate my education and collaboration with at Illinois from C.T. Sa, Greg Stillman, Nick Honiak Jr., and John Bardeen. And at University of Illinois, I produced 45 PhD, many of them in Taiwan for do productive work, I guess, right? And the 5 is still in progress in my laboratory. Truly supported by National Science Foundation, Semiconductor Research Corporation, DARPA, IARPA, and Army, Air Force, and ONR Navy. And many companies support that. Collaboration with the National Taiwan University, and very appreciate the work with Professor Guangru Lin and Xie Chu and J.J. Huang. Thank you. This is the end of my talk.